Well, out of above 5 possible combinations of inductor, capacitor and resistor as shown in 5 circuits, number 5 is the Lcr series circuit that we have already discussed. Now the circuit number 2 is effectively a resistive circuit. The circuit number 3 is practically not realizable as because of series resistance of pure capacitor is 0. As we have seen, the power factor which is cos phi vanishes. Circuit number 1 and circuit number 4 are equivalent circuit which can be confirmed by series to parallel conversion formula, and hence these two circuits are called Lcr Parallel Circuit, and subsequently circuit number 6 and 7 we will see which are more realistic Lcr Parallel Circuit in our day-to-day life. Now in analysis, if you see to the circuit number 1, then Z1, which is the impedance of the resistor and inductor, can be written equal to R plus J omega L. Z2 is the impedance of the capacitor, which can be written as equal to minus J times 1 upon omega C, that we can write as equal to 1 upon J omega C. And obviously the negative sign ensures here that XL and XC are opposite in phase. So therefore the effective or the net impedance due to the combination of Z1 and Z2 which are in parallel can be written as equal to Z. Since they are parallel, we can write 1 upon Z is equal to 1 upon Z1 plus 1 upon Z2, which we can be able to write that Y is the admittance of the circuit. That can be written as equal to 1 upon R plus J omega L plus 1 upon again J omega C, which we can write equal to 1 upon R plus J omega L plus J omega C. We can multiply in the numerator and denominator of the first term, that is R minus J omega L, to write the admittance equal to R minus J omega L upon R square plus omega square L square plus J omega C. The 1 upon Z2, which is the admittance, can be written in phase manner and in quadrature manner as equal to R upon R square plus omega square L square, one term, that is the phase term, plus J times within bracket omega C minus omega L by R square plus omega square L square, which is the quadrature term. The current I can be written as E by Z, which is equal to E times the term which we have mentioned, that is R upon R square plus omega square L square, and second is J times omega C minus omega L by R square plus omega square L square. And theta is obviously tan inverse of the ratio of omega C minus omega L by R square plus omega square L square upon R whole upon R square plus omega square L square. The magnitude of the current I we can write as equal to E0 times entire square root of within bracket R by R square plus omega square L square whole square plus within bracket omega C minus omega L by R square plus omega square L square whole square. What happens at resonance? From figure 1, the current drawn from the source is minimum, and hence quadrature part needs to vanish. So that is omega 0 C minus omega 0 L by R square plus omega 0 square L square must be equal to 0, which on simplification will give omega 0 is equal to square root upon 1 upon LC minus R square by L square, which is called the resonant frequency, and effective contribution due to reactive component at resonance vanishes, and current from source is not allowed into the reactive component, and this is the reason why Lcr parallel circuit at resonance condition is known as rejector circuit, as because the current is rejected. To enter from the source, the current is rejected. The opposition to inflow of source current at resonance is called dynamic resistance, or it is called parallel resistance also, which is the reciprocal of real part of the admittance. Therefore, we can write the dynamic resistance or the parallel resistance equal to R square plus omega 0 square L square upon R, which on substitution of omega 0 we can write equal to R square plus within bracket 1 upon LC minus R square by L square times L square whole upon R, which will give us L by RC. The current drawn from source at resonance, which is also known as makeup current, can be written as E0 upon L by RC, which can be written equal to E0 RC by L. This makeup current is 0 if the resistance vanishes, which is a case of an ideal case. But in practice, the resistance is small and the source current and voltage are in phase, but the oscillatory current, if you see through the capacitor and inductors, are out of phase. That the oscillatory current through capacitor can be written as IC equal to E0 upon 1 upon omega 0 C, which we can write down omega 0 C E0. Similarly, the oscillatory current IL is equal to E0 upon omega 0 L, and this IC and IL are out of phase. So therefore, if you see the ratio of oscillatory current to makeup current, which you can write, that is IC by I0 and IL by I0, they are equal. That is equal to omega 0 L by R, which is equal to 1 upon omega 0 RC. And at resonance, these oscillatory current is magnified. IC and IL, these are magnified, as because if you see to the ratios, it is always very greater than 1. It's because omega 0 L by R is very greater than 1, and 1 upon omega 0 RC is also very greater than 1. So therefore, these oscillatory current appears as magnified currents over the makeup current which is drawn from the source, and hence this is called a case of current resonance. And at resonance, magnitude of capacitive susceptance is equal to magnitude of inductive susceptance, that is BC mod is equal to BL mod. If you see to the figure, the variation of inductive susceptance and capacitive susceptance is as so. That is, capacitive susceptance BC is directly proportional to frequency, and after resonant frequency, this capacitive susceptance dominates the circuit, and hence admittance increases with the increase of frequency beyond resonant frequency. In inductive susceptance, if you see, which is inversely proportional to frequency and within the interval of 0 to resonant frequency, this inductive susceptance BL dominates the circuits, and hence the admittance decreases with the frequency within the interval 0 to resonant frequency. The circuit admittance varies in the same manner as the current drawn from the source, that is, it increases, the circuit admittance increases on either side of the resonant frequency omega 0, and at the resonant frequency, if you see, the circuit admittance is equal to the circuit conductance, that is Y equal to G. Now regarding phase, if you see only at resonant frequency omega 0, the source current and source voltage are in phase, and if you exclude omega 0, that is the resonant frequency, the phase is driven by values of L, C, R combinations with source frequency. And coming to power distributions in DC, if you see the product of voltage and current giving steady power in direct current, but in AC, the power distribution is decided by the resulting phase of the voltage current product. And as we know, the power distribution is only due to resistor only. It is because cos phi, which is the power factor, is not to be equal to 0, is the condition for power distributions. For example, if you take phi equal to 90 degree, in that case cos phi will be 0, and then power distribution is minimum, and the corresponding current is called wattless current. Therefore, the average power distribution, which we can write down P average equal to E RMS I RMS times cos phi. That can also be written as E RMS square upon R times cos phi. So therefore, this average power distribution will be simply equal to E RMS square by R at resonance frequency. It is because cos phi at resonance equal to 1, which is maximum value, in the form of joule heating through the resistors. That means at resonance, these power distributions appears only on the resistors. The power distribution curve is shown accordingly in the diagram, you can see. Coming to quality and bandwidth, the maximum energy stored by the capacitor we have seen is half C V0 square. Energy dissipated in a complete cycle must be equal to joules heat in resistor times the period of the source. So therefore, the quality we can divide as Q is equal to 2 pi times maximum energy stored per cycle divided by energy dissipated per cycle. So that is equal to 2 pi times half C V0 square upon E RMS square by R times T0, where T0 is the cycle of the source. This quality can be equal to 2 pi F0 times C V RMS square upon E RMS square by R, where we have used the concept V RMS is equal to V0 by root 2, and therefore the Q can be written as 2 pi F0 times RC. It is because at a resonant frequency, V RMS is equal to E RMS, and therefore the quality factor, which is equal to omega 0 times RC, can be written as equal to R upon XC, where XC is the capacitive reactance, that is equal to R by XL, because for an ideal Lcr parallel circuit, L is pure, that is it never possesses any resistance. So therefore, we can write the quality factor Q equal to R upon omega 0 by L, and on substitution of omega 0 as 1 by square root of LC. Quality factor equal to R upon square root of 1 upon LC times L, which will give us Q equal to R times square root of C by L. But for non-ideal, which is a real Lcr parallel circuit, if you see the quality factor, we can write Q parallel is equal to omega 0 times C times R equivalent. That is equal to R equivalent by omega 0 times L parallel. That is equal to R equivalent times square root of C by L parallel. And where the equivalent circuit with its components are shown using series to parallel conversions with the formula, that is R parallel is equal to R coil square plus X coil square upon R coil. XP is equal to R coil square plus X coil square by X coil, and the R equivalent is equal to R times RP by R by RP. The bandwidth for Lcr parallel circuit is well defined only at resonant frequency, equal to F0 by QP, and beyond this resonant frequency, the response curve is unsymmetrical, and hence the concept of bandwidth ceases. Resulting current triangles using phasor for the equivalent Lcr parallel circuit are as shown for the three cases, that is when the capacitive susceptance is equal to the inductive susceptance, when the capacitive susceptance is greater than the inductive susceptance, and the capacitive susceptance is less than the inductive susceptance. We will discuss more about the LCR circuits in our subsequent class. Thank you.